Welcome to a lesson with Dr. Powell. In this video, we're going to extend what we've discussed in the previous two videos about how to define sine theta and cosine theta, and secant, tangent, cosecant, cotangent from some similar triangles with a 1 on one of the sides, either hypotenuse on the adjacent or the opposite, and how we can use that to write down some formulas or to write down a formula in a given situation. It'll just be an example of that. So in the last video, we walked through how we can, for specific triangles and angles, if we just know one of the sides, how we can get all of the side lengths in based off of that rather quickly. Now here, maybe we want to figure out a formula for the side lengths of the big triangle right here. So you have hypotenuse, maybe this side, maybe that side. Let's kind of think of some ways that we could come up with some formulas for this. Let's start off with hypotenuse, coming up with the formula for the hypotenuse in terms of the angle theta, as theta varies, but this side length 6 and 4, those stay the same. How is this hypotenuse is going to be changing, and as well as this length right here, as well as the bottom, and we could say even the bottom length. It's going to depend on theta, and how so, right? What's a nice formula for that? Well, first of all, we one way of thinking about this is we could just look at this triangle and say, well, its hypotenuse is what? It looks like a 6 is opposite, and so we're thinking of a 1 right here and a theta. What trigonometric functions deal with a 1 right here on that side? That would be the cotangent and the cosecant. So using this similar triangle idea, but noticing the 1 is replaceable with a 6, we know that the hypotenuse is a meter of this smaller triangle right here is 6 cosecant theta. We want a formula for the whole thing, right? So we can, in our mind, we can think, okay, we have a right triangle right here with a side length of 4, and we also have an angle theta. This line's parallel to that one. That angle's the same as that one. So you could think, okay, well, so side length with, instead of a 4, think of 1. You think, okay, and maybe we'll make that a little straighter here. All right, so this side length would be, if that's a theta, this would be tangent, and this would be secant. Okay, but since this is a 4 instead of a 1, you could say 4 times 4, 4. So 4 secant theta would be this length right here. So if we wanted a function that represented the hypotenuse, the big hypotenuse of a triangle in that situation, you could write something like this: f of theta is equal to 6 cosecant theta plus 4 secant theta. So we have a formula. And oftentimes in calculus, in given situations, you want to find a formula for things based upon a parameter that's altering or changing. So you have a function to work with, especially if you're trying to optimize a particular situation or something. Having a function is a first step. So, so you can have a formula for the hypotenuse of the big triangle. We could also find a formula maybe for, let's say, for this opposite side. Let's try that. There's a couple ways that we could do this. So this opposite side right here, we could automatically say, well, it's going to be 6 plus this length. And this length will simply be, looking at this triangle right here, 4 tangent of theta. So we could have another function, g of theta is equal to just 6 plus 4 tangent theta. 6 plus 4 tangent theta. Now we could have done this in various ways. I mean, we could have started off by saying, hey, this side length right here is, based upon this triangle right here, would be 6 cotangent theta. So this whole side length is 6 cotangent theta plus 4. And then what you could have done is you could have said, okay, think of this as being like a number. And so then this opposite would be like that number times tangent theta, and this whole hypotenuse would be like that number times the secant of theta, using kind of a similar situation to this. And instead of a 4, you would be thinking of 4 plus 6 cotangent theta, and just multiply that to tangent theta or to secant theta, and you should get the exact same thing. I mean, we could try it out if you want, and I think it's good just to kind of see different ways how this might go. So if this bottom length right here is, let's see, is 6 cotangent theta plus 4, then using a triangle where you have 1, this is theta, this is tangent theta, this is secant theta, but instead of a 1, you have this, so you just multiply all the side lengths by 6 cotangent theta plus 4. So in particular, this side length, the opposite, will be tangent theta times this. Now what happens when you multiply tangent theta into here? Okay, so you're going to get 4 tangent theta, and then we're going to get 6 cotangent theta times tangent theta plus 4 tangent theta. Now realize that tangent, and so the cotangent of an angle and a tangent of an angle, kind of how they're defined, they kind of crisscross of each other. You know, if you have the angle 1 here, and so forth. In fact, they're actually reciprocals of each other. It's kind of a reciprocal notion. You're changing where it's like, you know, like 1 to cotangent theta should be the exact same thing as tangent to 1. I mean, which actually tells you they're reciprocals of each other. Tangent theta itself, which is what that is equal to 1 over cotangent. So you can kind of see, because these two triangles, if you have theta here and theta here, they're actually similar to each other. And if we knock off and I'll just do this real quick. If we knock off these extra numbers, the 6, 6, and 4, 4, see if I can 4, okay. So if we knock those off, then these two triangles, even though they have different numbers here, are similar to each other because they share the theta, if theta is the same in both theta and the right. Okay, so they're similar, which means that this to this is the same as this to this. So 1 to cotangent is the same as tangent to 1, which gives you this reciprocal notion. So tangent is the reciprocal of cotangent, 1 over. So you can replace tangent with 1 over cotangent, and look what happens. You go to cancellation, you'll end up getting the 6. So this whole part cancels, and you get 6 plus 4 tangent theta. So now, similarly, you could have taken this whole expression, 6 times cotangent theta plus 4, and multiplied it by secant. By secant of theta. So, right, because if you multiply all the side lengths of this triangle by this, we just multiply the tangent by it. But if we multiply it to the secant, we'd actually get this through distributing. And let's just take a look at that. So we get secant theta times 6 cotangent theta plus 4. Now notice when this multiplies through 4 secant theta, hey, that's what we have here. 4 secant theta, right? Then we multiply it through, we get 6 cotangent theta times secant theta. Now, let's think about that. Let's see. 6 cotangent theta times secant theta. Is that going to be equal to cosecant? Now, it will be. It will be equal to it, and we can again think about ratios on triangles. For instance, let's see, the ratio of secant, for instance, the ratio of secant to 1 is the same as the ratio of cosecant theta to cotangent theta, right? So what happens if we multiply both sides of this relationship by cotangent? You would end up getting cotangent times secant, right? Cotangent times secant, which actually is equal to cosecant. Ooh, so this is actually the exact same as cosecant. So you would end up getting the exact same thing. Now, why would you want to do it the harder way? Why can't you just do it the way that we did at the beginning? Well, please do it the way we did at the beginning. I only pointed this out in case you get lost and you keep trying to do different things. My point is, you should equivalently get back to the same thing if you're doing these similar triangles appropriately. There is often a faster and simpler way of writing things down, and I encourage you to do so. But please keep in mind that all these ideas relate and can work together in such a way. Thanks for watching.